Hello. So in this video, we are going to be talking about horizontal asymptotes. So horizontal asymptotes, these are sort of horizontal lines that the function sort of tends to as the x value gets really large in either direction, like positive or negative, right? So we remember this from way back, right, in the general functions section. So the way that these occur in sort of the context of rational functions is about relative growth rates. So this is the sort of real-ish answer, but it turns out, maybe unsurprising at this point, that we need calculus again in order to do this sort of in the real sense. So we're going to have sort of a particular case that we're going to talk about. But before we get there, we're going to explain sort of this higher level idea for rational functions. So when I talk about relative growth rates, what I mean is how fast does f of x get big versus how fast does g of x get big? And there's really three possibilities, right, relative to each other. Either the growth rate of f of x is just bigger than the growth rate of g of x by some important sort of real amount. What that means exactly is very vague without calculus. Another possibility, growth rate of f of x is smaller than the growth rate of g of x. So right, in the first case, right, in the orange case, f of x is getting much bigger, much faster than g, whereas in the purple case, right, the f of x is not getting big relative to g. So g is getting much bigger, much faster. And the third case is when the relative growth rates are roughly the same, meaning that one might be growing faster than the other, but it's growing faster by some sort of steady amount, right? So they might grow faster. It might grow twice as fast, but it's not growing sort of infinitely faster. And that's sort of the case in the first two. So in the first case, when the growth rate of f of x is sort of infinitely faster than the growth rate of g of x, there's no horizontal asymptote. And that's because the top part is just sort of shooting off such a high magnitude so quickly that the bottom part can't do anything about it. So it just gets really big really fast. Nothing bringing it back down to have a horizontal asymptote. Now, for the purple one, right, when g of x is the bottom, g of x, is actually growing infinitely faster than f, well, now you're dividing by something that's getting really, really, really big, really fast, much faster than the top. And so you end up with this sort of number being divided by some way bigger number, and the bottom is just getting bigger infinitely faster. So everything gets crushed down to zero. Because no matter how big the top gets, the bottom is just like way bigger and going infinitely bigger. Now, in the case where they are roughly the same, meaning that one is sort of twice as big as the other, but it's not infinitely bigger, well, then the horizontal asymptote exists, and it's a ratio, whatever that ratio is. So if the top is twice as big as the bottom, well, that means that the actual horizontal asymptote will go to 2, right? Because you get twice as much of a growth rate on the top versus the bottom, so you get 2 over 1. You get y equals 2 as your horizontal asymptote. So again, if the top is getting bigger, sort of infinitely bigger than the bottom, no horizontal asymptote. If the bottom is getting infinitely bigger than the top, you have an asymptote at 0. And if they're getting sort of big at the same rate, even if they're both going to infinity, then the ratio of how fast they're going to infinitely large values, that's what you get for an asymptote. Now, this is all very vague, right? Like, what's it mean to be getting infinitely bigger or something, right? And unfortunately, this is the part you need calculus for. But when it comes to specifically where the top and bottom are polynomials, then it's sort of much easier because you have this nice little trick that wherever the highest power is, that thing wins, right? So if you have something like 3x squared plus 2x minus 1 over 6x cubed plus 2x plus 1. The degree of the top is 2. The degree of the bottom is 3. 3 is bigger than 2. I know, crazy. So the bottom wins. That is going to be infinitely bigger. So this is going to have a horizontal asymptote at 0 because the bottom is the one with the larger growth rate, right? It's getting much bigger, much faster because the bottom has a higher degree, okay? If they were flipped, right, so that the cubic was on the top and the quadratic was on the bottom, then the top would have the higher growth rate, and then there'd be no horizontal asymptote. It'd be like the orange situation. So this one is like the purple one where the bottom is much faster because the bottom has a higher degree. If they were flipped so that the top and bottom flipped sides, you get something like the orange situation and you have no asymptote. Now, again, in contrast, if they have the same degree, well, then they are growing at roughly the same rate. So now it's like the green situation where the parts that actually matter are whatever those leading terms are, meaning the terms that are the highest power, right, that match the degree. So in the top, we have 3x to the 6th plus 1. So the leading term is this 3x to the 6th. Bottom, bunch of terms, but the leading term, right, the highest degree is this 2x to the 6th. These are both the same degree, so you get a horizontal asymptote that occurs at that ratio, meaning it would be something like 3x to the 6th over 2x to the 6th, which is just 3 halves. So this would have a horizontal asymptote of y equals 3 halves. Okay? All right. So what we do? Well, we talked about horizontal asymptotes, and in particular, we talked about how horizontal asymptotes are really this sort of have to do with the ratio of the growth rates, and how if the top is much faster, like infinitely faster, you have no horizontal asymptote. If the bottom is infinitely faster, everything gets crushed down to 0, and if they're growing at roughly the same rate, then it's the ratio of the two that gives you what the horizontal asymptote is. Granted, these are sort of very vague statements without calculus to really nail down what we mean by these terms, but if the top and bottom are just polynomials, and that's key, right? They have to be polynomials, but if they're polynomials, then we can use the degree to tell us. It's sort of a substitution for that idea of growth rates. So if the top degree is higher, no asymptote. If the bottom degree is higher, we have an asymptote at 0. And if they're the same degree, then we take the ratio of those leading terms, or really the ratio of the leading coefficients, and that gives us the horizontal asymptote. Okay? So that is that.